Okay, so if not, we can finish the class in about 15 minutes, I think. So previously we were speaking about how to model different types of patterns as RDF graphs. And we spoke about the use of blank nodes for things like lists, which you will also see in the lab. So blank nodes can be useful for modeling more complex types of data where we don't need to identify every node with an IRI. We can leave some as blank nodes. So there are some complications associated with blank nodes. And somebody asked this question in the last class, in the class on Monday, about what happens if we have two different documents or two different RDF graphs that use the same labels, or do the labels matter in the case of blank nodes? So here, if we have two different RDF graphs and two different documents, for example, and here we use B1 and B2 to identify some ingredients of lemon cheesecake. And here we use, not to identify, but to represent. And here we use two blank nodes with the same names to represent ingredients of pecan pie. So if we were to naively integrate these data by taking the union of the graph, of the two graphs, essentially taking the unions of the sets of triples, we would end up with a graph that might look a little bit, that would look like this. So essentially we would consider B1 to be the same as B1 here, and B2 to be the same node as B2 here. And then we would have that pecan pie and lemon cheesecake share two ingredients. One of those ingredients contains gluten and the other one contains both pecan and citrus, which is not the intent, right? So in fact, this would be incorrect. This would not be what we want. Rather, what we want is somehow to keep these identifiers as local identifiers. So what we should do is really rename these blank nodes to make them distinct in every graph. So here we'll just add G1 to the ones from graph 1, and we'll append G2 to the ones from graph 2. So we've got B1, G2, B2, G2, B2, G1, and B1, G1. And now we avoid this, what they call a blank node clash between the two graphs. So we avoid falsely combining these blank nodes as one node. And this seems to make a bit more sense. So maybe this might be flour and lemon, and this might be, well, pecan nuts, I guess, and this might be something else that contains gluten. So this is how we should combine two different RDF graphs with blank nodes. We should make sure to make their blank nodes distinct first, and then take the union of the RDF graphs. And this is called an RDF merge. So this makes more sense. So in some sense, we can say that the names of blank nodes are not important. They're kind of like variables in a programming language, or maybe variables in a query. We can kind of rename them in a one-to-one way, and it doesn't really change the meaning of the program or the meaning of the query. And similarly, we can rename the blank nodes in a one-to-one manner, and we don't really change the meaning of the RDF graph. So we see two RDF graphs here representing lists, which we previously saw. In this case, we have the blank nodes named L1, L2, L3, in this case, BX, BY, BZ. And there's a formal relationship between these two graphs that the RDF standard defines, which is, it says that the graphs are isomorphic. And specifically, the graphs are isomorphic if there is a one-to-one mapping of blank nodes that turns one graph into the other, right? So we can label L1 to be X, L2 to be Y, and L3 to be Z, and we'll get exactly the second graph, right? All of the other terms, the predicates or all of the IRIs and literals have to correspond exactly. So this is isomorphic in this case because we get exactly the same graph. If we were to change, for example, maybe the order here of the elements to say lemon, water, sugar, then this is not isomorphic because we can't map the blank nodes here in a one-to-one manner to the blank nodes here to get exactly the same graph. We'll have these elements in a different order. So this graph would not be isomorphic, for example. Okay, so the question then of, are two RDF graphs the same in some sense? And there's a couple of ways in which we can define are they the same, but one of the most common ones is to use isomorphism, right? Which essentially just disregards the particular labeling of blank notes. So these two graphs are isomorphic. If we look kind of closely, we see that we have lemon cheesecake has some ingredient that contains gluten and citrus. Lemon cheesecake contains some ingredient that has gluten and citrus, or gluten. And lemon cheesecake has an ingredient that contains citrus in this direction. So I've drawn the graphs a little bit differently just to be tricky, but we see that these two graphs are still isomorphic. Okay. What about this case? So, okay, here are, just for brevity, because it gets a bit messy, I've omitted the predicate, but we can assume that the same predicate is used in all the graphs, for example, P. So what do we think? Do these two graphs look isomorphic?
Maybe, because they don't mean nothing. They both have no significance.
Yeah, so in some sense, what we would need is to see if there's a way to map all of these blank notes in a one-to-one manner, such that we get the same graph. And okay, we can make some quick observations. We can see that there's 1, 2, 3, 4, 5, 6, 7, 8 blank notes here and 8 blank notes here. We can take an example here. This node has 2 inlinks or 3 inlinks. So maybe we can find some node here that has 3 inlinks. This one, for example. So maybe that's a candidate. A1 maps to X8. This one has 1 outlink and 2 inlinks. So maybe we can find an example like A5 has 1 outlink and 2 inlinks, and so forth. So we can maybe start to collect some evidence. But actually, this is a hard problem. If you were to even program this, this is not so easy. There's some tricks we can apply to make it easier. But okay, in fact, these graphs are isomorphic. So if we map the nodes with the same color between both graphs, we'll see that we end up with exactly the same graph. For example, this dark blue A8 maps to X1, in which case A5 becomes X4. Okay, dark blue is also connected to yellow here, and dark blue is also connected to green here. So we see that somehow through this mapping, we end up with actually the same graph, preserving all the nodes that are connected. So maybe red connects to orange and is connected to by green and cyan or light blue. So we have red connects to orange and is connected, and we can verify this for every node and is connected to by green and cyan. In general, just to give a kind of flavor of if we look at some examples, it looks easy, but this problem is actually hard. This problem is in a complexity class called GI complete, which, if you know NP and P, this is a rare kind of class that is an intermediate class, which means that so first of all, GI complete means as hard as graph isomorphism. And graph isomorphism is something that's in P, but is it's in NP, but it's not known to be in P. So nor is it known to be in NP complete. So it's somehow between P and NP, right? So it's not known to be as hard as the NP complete problems, nor is it known to be in P. So it's somehow a difficult problem that's not quite as difficult as NP complete, or probably not as difficult. So this is a difficult problem in general. And this is now just because of blank nodes. It means that whether or not two RDF graphs are the same, we have this GI complete problem that we have to solve. Of course, in practice, these sorts of graphs, they're kind of, like someone said, they don't really mean a whole lot, right? I mean, they're valid RDF graphs, and the notion of isomorphism applies between them, but they're not really very real world, shall we say. Okay, any questions or doubts about graph isomorphism or about
I have a
RDF graph?
question.
Yep.
We know that it's a hard problem to know if two graphs are isomorphic, but is there a way that two graphs that are not isomorphic can be altered or converted to isomorphic?
So if we have two graphs that are not isomorphic and we want to make them isomorphic, that would be similarly a difficult problem in the sense that, if you wanted to compute how many edits you'd have to make to one graph to make it isomorphic to another, that would similarly be a difficult problem, in the sense that at some stage you're finished when the two graphs are isomorphic. And this, you can reduce graph isomorphism to this. So you could say, okay, if this has no edits, if the two inputs are isomorphic already, then you say, okay, this has no edits, and you know that the two graphs are isomorphic. So somehow that procedure would be sufficient to solve graph isomorphism, if that makes sense.
Makes sense. Thank you.
Okay.
Sorry, excuse me.
Yep, sure, go ahead.
If, for example, I have like two documents that represent the same subject, and it could be really possible, I guess, that I can represent that information in two different graphs that have the same information, but different. I mean, both graphs are not isomorphic, but represent the same information.
Yep.
So what happens in those cases if I want to compare at a level of information between two graphs?
Yep. So there is a different level of comparison. This is really just comparing the structure of the graph. There is also, we can compare the semantics or the meaning of the graph. And that's something that we'll cover more in later classes. So essentially, we can try to figure out what the graph means, and we can try to compare graphs in that way. And there is a notion of semantic equivalence of graphs, where two graphs can have different structure, but the same meaning. We can do that, but it's limited to the kind of meaning we can define and we can process in machines. So what kind of meaning of data we can define. So this is sort of, this will be, so it's a very good question, but we will see that later in another class. And there are techniques for that. Limited techniques, but there are techniques for comparing graphs, not in terms of structure, but in terms of semantics or meaning.
I see. Thank you.
Okay. Yeah, so it's an important point that, okay, if they're isomorphic, we know that they mean the same thing, right? But if they mean the same thing, they might mean the same thing and not be isomorphic. So if the two graphs are not isomorphic, it does not imply that they mean different things, right? So, yep, but if they have the same structure, if they're isomorphic in some sense, they mean the same thing. Other questions or doubts? Okay, so it's important to note that RDF itself is like a data model. It's this abstract notion of graphs, right? Like we saw here. And there's various syntaxes for writing these graphs down. Okay. So I'm not going to bore you too much with the syntax. I'm going to focus on one in particular that will be later that we'll use in the lab. But the first syntax is n triples, where we essentially just write, here's the data that we're representing in every document. So we'll represent the same triples in every document you see here. It's this, in triples is the simplest format. It's just triple by triple. It has no abbreviations. It's very nice for processing in Unix or using grep or these sorts of line by line processing tools, because every line is a triple. We can even, concatenate n triples files to take the unions of the graphs. Okay, we have to be careful with blank notes, as mentioned before. So it's very easy to work or process this sort of data. It's not so readable because we have all this HTTP : / stuff going on, right? So, but we see that we just write out everything in full, all the IRIs in full, no abbreviations, no prefixes. RDF XML was sort of the original standard format. And this was probably one of the bigger mistakes of the semantic web, which was that they defined this format, and for a long time, it was kind of the only standard syntax for RDF. And it's kind of difficult to read or to understand. The idea was that XML was sort of a popular format at the time that was also kind of gaining popularity, and it was a standard web syntax. So the idea was to kind of leverage that, because there were all these tools for XML and so forth, to have an RDF XML syntax and to be able to use XML tools to process RDF. But in truth, the syntax is just very difficult to read the way it was defined. I'm not going to really get into too much detail, but the idea is that you have kind of nested, this is a subject, and then you have predicates, and they can have objects in different ways. And one of the problems is that there's many different ways to represent an isomorphic RDF graph. You could change the XML syntax around a lot and still end up with an isomorphic RDF graph, which means it was sort of useless for XML tools. It didn't really make sense, because an XPath query and one RDF XML document wouldn't apply to the other, even though the graphs were the same. So in general, the overall motivation for using XML was not really useful, and the syntax is just really horrible to read. So it was kind of a mistake, because people at the start of the semantic web, they did not like this format, and they thought it was XML. They didn't realize why you wouldn't just use XML. RDFA is particularly useful for embedding RDF into HTML. So this is useful for the kinds of use cases that we spoke about before, which is the rich snippets and so forth, where you can embed structured RDF data into your web page. So instead of having a separate page, one for your RDF data, one for your HTML human readable version, you just embed your RDF data into your HTML page. So we see here some extra metadata here, referring to different properties of a recipe. So actually here the data has changed. It's slightly different. We also have JSON-LD. JSON-LD is essentially a way of converting JSON documents into linked data, or into essentially almost RDF. It has some slight differences with RDF, but essentially we can consider it to be an RDF syntax, because those differences we can change. So what happens is essentially we define somehow a context. And the core idea of the context is defining how you define the IRIs, the identifiers for the JSON document. So essentially we add some metadata here, and this largely allows us to convert, this context allows us to convert a JSON document into RDF. We can also publish this context elsewhere on the web and refer to it. So we don't need to copy this into every JSON document. We can rather refer to a context elsewhere and use that in multiple documents. This has become quite popular as well. And finally, we have Turtle, which is the most readable format. It's also used for some of the query languages. It's the basis of the Sparkle query syntax. So we're going to use it in the lab. So I'm going to spend just a quick mention of what we can use. It's similar to n triples, but now we have a bunch of abbreviations that we can use. So the first we can use is relative URIs, which is where if we don't have a full URI or IRI, we can just use this and it will be appended to the base IRI here. So we can have, this would end up being gen. So this would be ex1.org/#gen, right? So first thing, We can have prefixes, which we've seen before. So we can define a prefix or RDFS or EX1, and then we can use those prefixes in this way. We have oftentimes when we're defining something, we'll be defining gen, and we'll define multiple triples about gen. So with a comma, we can give another object. Essentially, it says repeat the previous subject and predicate, which this is RDF type, and then give another object. So this is like subject, predicate, object, 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 right? The semicolon here says repeat the previous subject and predicate. So this would be, sorry, repeat the previous subject only. So this says, okay, we're going to say something about gen, right? So we reuse the same subject and we say RDFS label gen, allergy, citrus, location, etc. So this allows us essentially to define a bunch of things about these two shortcuts, allow us to define a bunch of things about the same subject, or to define multiple values for the same subject predicate. This is my favorite abbreviation of all, which is you can use a instead of RDF type. So gen a person. It's kind of how we would read this. And we don't have to give full data types here. We can just use numbers, and it will automatically interpret this as XSD decimal. We can, if we don't have a decimal point, it will interpret it as an XSD integer. We can also use true and false as shortcuts for Boolean values. And here, what is happening here, essentially, we're just creating a sort of a blank node. So what this says is the location is some blank node, and that blank node has latitude and longitude 53.3 and -9. So this is a kind of a crash course on the syntax. You'll see it in the lab in any case. I've kind of packed in a lot of abbreviations here into this part. So it's generally a little bit more readable than what I might see here, and you don't need to use all of the abbreviations. But so this has essentially these triples here, if you want to compare. Last shortcut that's very useful is for collections, or what we call lists. If I say lists, by the way, lists and collections mean the same thing in RDF. So how we would represent this in triples would be eliminate ingredients L1 and so forth. If we wanted to write it in Turtle, we could write it like this. So eliminate ingredients and then use this, create a blank node and then define some stuff and then create a blank node and define some stuff and so forth, which is kind of a bit ugly. Still, maybe a little bit cleaner. At least we don't have to create these labels for blank nodes. But Turtle provides a much more convenient syntax, which is using round parentheses, lemonade ingredients, and then round parentheses, sugar, water, lemon. So you can use this to very quickly define the ingredients of a collection. So this is only possible with blank nodes. So why is this only possible with blank nodes? Because if the blank node labels had meaning, we would have to name every node of the graph explicitly. So here, this allows us essentially to create a high-level syntax, and then we can fill in these blank nodes and give whatever labels we want to them. So RDF, any questions or doubts about Turtle? Okay, well, we'll practice in the lab as well. So in general, RDF, yeah, we've spoken about, this is the sort of agreed data model for the semantic web, for the web of data. It's a web standard, and it's quite broadly adopted. So this is an analysis, recent statistics about the number of websites using different types of structured data, publishing different types of structured data. And we see things like Open Graph, Twitter cards. These are essentially Facebook specific. This is a Facebook specific format, and this is a Twitter specific format that generate, if you link to a page on Twitter, it kind of tells Twitter how to generate a summary of what's on that page. Same for Facebook Open Graph. It's a bit of a pain that they're defining their own formats and they're so successful with that. But anyways, JSON LD, which is essentially RDF, generic RDFA. microdata, Dublin core, and micro formats. So specifically being RDF, we have JSON LD and generic RDFA. Dublin core often is described. It's a vocabulary that uses RDF. But all of these can be somehow represented as RDF. Even Open Graph, I believe, is often using sort of an RDF syntax. So we see that even though you might not have heard of RDFA or RDF before, or thought about structured data on the web, there's a lot of websites that are already using that, using these things. Questions? Okay, so we can swap back into Discord if there's no questions.
Sorry, by the way, can you please share a new link for Discord?
Sure, we can do that.
Thank you.
I'll put it in the forum in response to the previous Discord thread. Yep, okay, so sure, we can move to the Discord.